All right. So this is more or less the equation that we left with. So we have a structure vector, the vector that describes the interference between the fields from the different particles that is expressed in this double sum over all the particles, over all the particle pairs, basically. Q is then the geometry vector that describes the difference between the incident wave vector, the outgoing wave vector towards the detector. So basically the angle under which we are looking at the system, and RE and RJ are the positions of the particles. So you can see that there's also a difference vector, so it signifies that the exact position of the particles is not so important. It only matters how far they are separated. Of course, we encountered already a function that described that. That was the pair correlation function. Can someone describe to me what the pair correlation function was, or what it described, what it looked like? So if we had let's say some center particle in an ensemble here, we had a number of other identical particles, around it. What we can do is define a distance r from this center particle, and then at a distance r, so of course not in 2D but in 3D, simply count how many other particles we would encounter. So if we would do that, so let's say we would make the distance r, so that would be the distance of counting, normalize it on the diameter of the particle itself. If we would do that counting in a large spherical volume, and all these particles would be either very small or they would be allowed to overlap, just for argument's sake, then it would look something like this. So at zero separation, even if the particle is very small, there is almost no probability of finding another particle. If the distance gets very large, it's also not very likely. So it would look something like this. But if we now consider the situation where these particles are definitely not allowed to overlap, so they have a certain size, this is still normalized on the diameter of the particle. They have a certain size, they are not allowed to overlap. So what is the probability of finding another particle at exactly 0 r? Absolutely. What is the probability of finding a particle at exactly half times the diameter? 0. Yeah, because they cannot overlap. So there's going to be, if we would make this same analysis, so we would have this particle still, we would take a distance r, we would count how many particles we would encounter up until a distance, a separation distance d. So on this axis, that would mean r over d is 1. That would be 0 probability of finding another particle. So what would happen if we would go to the far end? So we have so the reference particle is over there, and the other particle is over here. I'm going to count that. How do you think that that graph will look like? So how would the graph look like in this limit? Yeah, it would go to 0, and it would actually go to 0 in the same way as this one goes to 0, because in the end, the distance is so large compared to the diameter of the particles, then they actually become kind of like point particles. So then it does not really matter. So that same function, of probability, likelihood of finding another particle, which had the shape, this shape, when the particles were truly point-like and you could place them anywhere, now has the shape 0 from over the distance to one of the diameter, the same here, and then then something in between, so that if the distance becomes a little bit larger than the diameter, then there is a finite probability of finding a particle. So here, this function is going to have some value. That's it could be something funky, or in the end, if the particle, if the distance gets large, we'll go to the let's say the limit again. What the pair correlation function does is it normalizes this restricted version, so where the particles cannot overlap. It normalizes it on the unrestricted version. So you basically divide these two curves. So still on an axis R over D. A bit confusingly, it has also the symbol G, so not the scattering and entropy, but we have R over D. So what is its value up to 1? So we divide the restricted one with the unrestricted one. So what is that? Value up to 1. So basically, it means it is this one divided by this one. Yeah, so it is 0. So any pair correlation function for these particles will be 0 if the distance is less than the diameter. Then if we go to the far end on the other side, yeah, it would be 1. So let's have 1 here. Then here, for larger distances, it will be 1. And then, of course, the question is what happens in between. Well, if the number of particles in this volume is not very high, so let's say of volume fractions less than 1% or so, then it will look something like this. So quite simple. Here it will go up to 1 almost, and it will stay constant. So then the pair correlation function would be just like a step function. And this is the one that we did in the calculator class as well. If you now increase the number of particles, you would increase the volume fraction, and the likelihood of finding another particle exactly near the reference particle will increase. And in the pair correlation function, that will mean that, which again, this is indicative of the likelihood of finding another particle. So that means that there will be a little peak here, showing increased likelihood. But in the end, the limits will be observed. So in the end, it will decrease. For larger distances, it will decrease again a little bit, and then fall into that limit. If you truly increase the number of particles, so that they almost have no choice but to be close to each other, because otherwise you can't fit them into the sample. Then the likelihood of finding a particle at a distance less than the diameter is still 0. That never changes. But the likelihood of finding one exactly next to it, really think of a full bucket of marbles, is almost is very high. So that means that in that case, the pair correlation function value will shoot up very high, and also that the probability of finding a particle at 2 times the separation of 2 times the diameter will also be really high, because you have one particle here, a second particle almost certainly has to be very close to that. And then then if the bucket is really full, then it also for 2 times the diameter will also be. So what ultimately you will see if you keep increasing the volume fraction is something that oscillates. So again, with decreased likelihood for anything between 0 and 2 times the diameter, but with increased likelihood around 2 times the diameter. So my drawing is not so good. And then etc. Good. So at 3, you would also see a peak in between. It would be the probability would be less, and then in the end, it would tap out. A little bit of the trouble of thinking of particles that are on a line or in a plane is that this is, of course, a 3D problem. So that also means that the more your distance increases, so you have a little bit more options to place the next particle and the next particle. So in the end, it will then. So this was the pair correlation function. So this actually describes one of the things that we were talking about in that equation on the board there. So in the argument, in the complex argument of the exponential is the separation between particles. And this function here tells us how likely these separations are. So for a very high volume fraction, it is very likely that these separations are occurring at let's say multiples of the diameter. If it is a very low volume fraction, then it's very likely that, well, it is certain that there is no separations less than diameter, but it is the other separations are almost equally likely. So somehow, that is an intuitive argument at this moment, somehow this pair correlation function and this structure factor, or at least how it translates into the scattering properties, should have some connection. So we saw now in the previous hour that the structure factor ultimately will determine what the light scattering properties are. As an argument of the structure factor, we have distances between particles, and we also have a function that actually describes the likelihood of these distances. So I'm not going to derive it. That is way too much for now. I'm just going to give you the results, and I can put a derivation on Canvas if you like that. Yeah, this would be the relation. So the structure factor, again on the left hand side, and the equation on top, and the pair correlation function here in green, G of R, are related through a Fourier transform relation. I call it a Fourier transform relation because it is not a full Fourier transform. So you can see that you would have to subtract 1 from the pair correlation function, then take the Fourier transform. That's what this exponential here does. The Fourier pair is Q, that we encountered already. R in this case is it's just a spatial variable, which is also argument here. So you would take that Fourier transform, you can multiply it with the density and add 1 back. You would have the structure factor. The derivation, I'm not going to, if it's okay with you, I'm not going to do the derivation because it's a mathematical, it's really a mathematical thing, and maybe it's just best for you to just read it, and if you have any questions, then I'll be happy.
Zeg het maar. Rustig gewoon, niet schreeuwen.
There's a few good things, or a few simplifications that we can make. So if the medium is homogeneous and isotropic, so homogeneous means that the properties are the same, properties like average density or so are the same no matter where you look. If it's isotropic, that means that no matter under which angle you look at it, it will have the same properties. Then G of R will be R will not be a vector, but just be a scalar. We do just the distance, so it becomes a 1D one-dimensional. That's fine because then also the Fourier transform will become a one-dimensional scalar. So we don't have to do any complicated calculations. So Q, just as a reminder, Q was 2k times the sine of half the scattering angle. So that describes the geometry of the experiment. Rho was the volume fraction divided by the volume of the particle. Basically meaning that we can also substitute that, so that means that we can express the structure factor as well as a function of theta. So instead of Q, we can use theta. Instead of rho, the density, we can use the volume fraction. So that this is meant to show that there is equivalence that you can express it. So here, this is what we just did on the board, so I'm not going to repeat this. This is the graph now neatly written, neatly drawn for the pair correlation function at different volume fractions. So the blue one is for a high volume fraction, but you can see these peaks occurring at almost at multiples of the particle. If we then calculate the structure factor from it, so we can take that Fourier relation, we can make that transform. Then that would also yield plots for the structure factor. And what you'll find is that we put here. So the Fourier pair was S of Q of the pair correlation function is a function of distance to S of Q. That is not really practical. It is more beneficial to normalize the distance and the diameter of the particle. That is what we already did, and that leads to also a normalization on the Fourier conjugate axis, so the Q axis as a multiplication of T times Q. The good thing about that sounds a little bit complicated, but the good thing about this is that this is a normative graph. You can always use that regardless of the value of D. So you can just for any value of D, you can just look up or scale the axis, and you would get the same result. What you see is that for low concentrations, that is the 0.1%, that corresponded to this step function like a pair correlation function. If you calculate it, you will find that it is almost unity, the black curve here, almost unity over the whole range. If it is almost unity, if you remember how it was included in the integrations, then it means that it does not really do anything. It's also almost neglected. So for the low concentrations, what it shows is that for the very low concentrations, these interferences, as expressed by the structure factor, as expressed by the pair correlation function, do not really matter. Because if you start to increase the volume fraction, let's say to 20 or 50%, as it described, you see that actually there are changes in the structure factor, so less or unequal to 1 for high concentrations. That would be put into the equations, and that will lead to and you cannot neglect it anymore. These are the same graphs. So let's take a look at a few practical examples. I have calculated the following graphs that I will show is a calculation of the scattering coefficient of a medium. So just taking spheres of a certain size, illuminated with a certain wavelength, assuming a certain refractive index, just as you would go about, and then calculate two optical properties using mean theory. Mean theory was the theory that was valid for spheres of all sizes. So I calculated first the scattering cross section of such a particle, using meteor and then multiplied it with density, just linear scaling, and that is what you will see in blue. Well, let's call it independent scattering, so ignoring all these interferences. So that would be the blue part of that expression. The second one, or the second curve that you'll see, is again meteor used to calculate the scattering properties of one single particle, but then using the structure factor S of theta and phi over there to account for these interferences. So in this specific case, the pair correlation function derived with Perkins and Levick was used, and that was Fourier transformed into the structure factor. So that is what the details. But the difference between the red and the blue curves would be then that the red curves take into account interferences and blue curves will just ignore them. So for a single particle using meteor, you can calculate a phase function. We could. I'm a little bit hesitative about this point because I'm not even sure if it is truly valid if we do this. But so for a single particle, the phase function is defined. That is just the angular redistribution of the light. So you can calculate that. So now let's say we want to calculate the angular redistribution by this number of particles, this ensemble of particles. So we could define an effective phase function for the set of particles, and the way to do that would then be to multiply the phase function of that one particle with the structure factor, that would be the denominator here, and of course, because the phase function is normalized, we would divide it. Math is easy. You can always, even if it's not valid, you can still calculate it. So let's go. The checks that need to be in there, of course, is that if we go to low volume fractions, then the structure factor would go to unity. So then we would see no real difference between blue and red curves. They should go to their, let's say, independent. So here is the result of a simulation of let's see, a 500 nanometer radius silicon sphere. So I took the refractive index of silicon. I think it was illuminated with 1 micrometer light. So the wavelength two times the value of the radius. Here in this graph, you see the first data points here already. So for blue, that would be the meteor, where no interferences are taken into account. And already here, even for this low volume fraction, you see that taking the interferences into account leads to a lower value of scattering coefficient. So this is as a function of volume fraction. I'm going to increase that volume fraction as we go along. So that is for the scattering coefficient. If we look at the angular redistribution of light, that is on a polar plot, so that requires a little bit of interpretation. The light is coming in along this direction, Kn, so it hits the particle here, and then this orb tells us how much light is scattered into given angles. So this would be here would be totally in the forward direction, and then as you go along that polar plot, it is symmetrical. What you do see now here is that for this low volume fraction, that this redistribution is not it changes a little bit, but not it is not much different yet from the single particle. Okay, now let's increase the volume fraction to 0.1%, to 0.15%, to 0.2%. Anything you notice? Describe this. Does it make sense? let's then look first at the graph of the scattering coefficient as a function of volume fraction again. So along this axis, we have just increased the volume fraction, meaning we have just increased the number of scattering particles in it. So what do you know? What do you notice about the blue line? Yeah.
More than the
So yeah, so really, because that is what this calculation said, it just calculates the scattering coefficient of only one particle, then just scales the increase. So if I double the number of particles, then the scattering coefficient will double. That's what you see here. So linear scaling. It's a little bit subtle, but what do you notice about the red line?
And so we have, I think, this structure too. So that's why we lose part of the. We have less scattering compared to without the interference.
Yeah. So I think what you see here, at least now, is that it still increases. So if you add more particles, you will still get more scattered light. So the scattering coefficient does increase, only at increasingly shallow rates. And most important observation is indeed that it is always less than so you get your effective scattering coefficient is much less than what you may have expected just by taking one particle and then scaling it linearly. Then for the phase function, for the polar plot. So for the distribution, let's call it the distribution of the light over the different angles. What do you notice there? I'll go a few slides. I'll step through it again. That is maybe then. No. So this is where we started. Now I'm going to again increase the volume fraction. So 0.1. Now look at the polar plot. 0.15, 0.2. I can go on. 0.3. So you said much wider. That is true. What does that mean? What does that mean? Is that,
light directed in more angle.
Yeah, exactly. That was exactly the answer I was looking for. So here we have a particle that scatters. So it scatters light mostly. So light was remember it was coming in from the along the 180-degree line. So most of the light in blue is scattered in the forward direction. It's a little bit diverging, of course, but most of it is just predominantly the forward direction. And what you see now here is that the spread, the angular spread becomes much wider here in red, and you even see some light being scattered back. So that's qualitative observation, but the important, let's say the message is that the more pronounced this effect gets, as you increase the volume fraction, it not only affects the strength of scattering. So let's say the strength of scattering is then expressed by the scattering coefficient. It also affects how the light is redistributed. This is not just a theoretical construct. This has also been measured. So this is an old. So if you can read it, this is an quite old paper in applied optics where they took milk in big buckets of different dilutions, different concentrations, and then measured fibers, light in, light out, calculated the scattering coefficient from that, and plotted that as function of the volume function. And what they found are these data points here. Fitted the light to it. If you see data, fit something to it. That is the equation over here. That has no real physical meaning. But if you would have the linear scaling, and I drew that, of course, that would be the blue one. So yeah, we actually see this in experiments. It is not something that is just a mathematical construct. The funny thing is, though, that at the time, so in 2003, it was not understood why this happened. Strangely enough. So that's, but now we know. I want to give you a practical example of that, and that is blood scattering blood. Do you know what volume fraction of red blood cells in blood is? Approximately
50%.
Then you would probably have to report to the doping authority. But yeah, that is you are close. Yeah, I think for 45% is the normal value for males, and then for women. Let's say 45%. On that scale that we drew, that went to 20% or so. So this volume fraction is huge. Do you know what the size of the red blood cell is? Approximately.
I think pretty big compared to things in light.
Yeah, so let's consider visible light. So take let's say 800 or 600 nanometers, something like that. So that would be light emitting. But what is the so the size does not depend on the light, of course. But what is the size of the? Yeah, a few. Yeah, so it's in the order of radius of 3, I think, something like that. So it is almost in any case much larger than a wavelength. What do we expect when a particle is much larger than a wavelength in terms of redistribution of light? Yeah, so most of them, so the scattering is, I'll translate it a little bit. Most of the light is scattered in a forward direction. That means it's going to be difficult to distinguish light that has been scattered and light that has been transmitted, but most of the light is just carrying on. Okay, so that is something that we would know from. So if we would take a single red blood cell and then assume that it is almost spherical, we could take me theory, for example. We could calculate the scattering cross section. We could calculate the phase function. Most of the light would be scattered in forward. Okay. Basically, this is the same equation that you already saw, so that we don't need to dwell too much on it. We can do the same red and blue distinction again here, so we can calculate it for an individual particle or an individual red blood cell, and then in red take into account the structure factor or these differences. Or this is just a summary slide that comes a little bit too soon even. If we look at independently scattering particles, we would have a scattering coefficient that is the density times the scattering cross-section, and then in this case times a factor that by definition normalizes to unity. That's the true case is if you do take it into account, then the first part remains the same. The second part, the second integral includes structure factor, and only for low volume fractions, the structure factor will be reduced to unity and then come back. But it depends, and that is that's not even clear from this equation. The structure factor depends on the volume fraction. So the higher the volume fraction, the more pronounced the structure factor will be. So we did this. We tried to calculate this. Now, this is tying a few things together. You remember hopefully the discussion we had about causality. That if you knew the absorption coefficient, you could calculate the refractive index, or vice versa. Well, the absorption coefficient is something that is easy to measure. experiment. The refractive index not so much. So what we did is we took the absorption coefficient, applied the Kramers-Kronig analysis to calculate the real part of the refractive index that we didn't have there. You see the scaling data points as well to have it at the right value. So that was I think the result I've shown. I'm not sure if I showed this one as well. It was a little bit newer. It's a little bit higher wavelength. And we can use this as input for let's say meat theory to calculate scattering coefficient. So what you see here in this graph is the solid curves in red and blue are mean calculations for oxygenated hemoglobin, that is in red, and deoxygenated hemoglobin, that is in blue, using just theoretical, just using the absorption coefficient, doing the Kramers-Kronig, and then doing a mean calculation just to see if that works. So that's for the scattering coefficient on the left-hand side, for the anisotropy of the phase function, the G value on the right-hand side. Also shown is the same calculation basically, but then with a different refractive index. So a measurement of the refractive index by a different group, just to see how that. So same question again. Throwing a graph in your face, and my question is, what do you see? What do you notice? Is there anything strange? Is there anything? Let's start with the scattering coefficient. Any first observations?
I'm a bit confused. Is the scattering, the G, is the result of the Kramers-Kronig relation of the scattering coefficient?
No. These are two outcomes of the complete calculation. So we can look at them independently. So let's park this for a moment and just focus on the scattering coefficient. So again, the way this graph was originated is you take the absorption spectrum, do a Kramers-Kronig analysis, and you get the real part of the refractive index. You can put that into meat theory and calculate the scattering coefficient. And that is the black, the red and the blue line here. The gray line here is using experimental values for the real refractive index obtained by the. So the calculation is the same, but the input data is different. So one of the things that struck us a little bit is that there actually is a difference between the scattering coefficient between oxygenated and deoxygenated hemoglobin. We knew, of course, that there was an absorption difference, but we did not. Or it was not widely expected that there would be a difference in the scattering coefficient as well. The reason for that is that people until 10 years ago, 20 years ago, did not really realize that these two are really intimately connected. So that was it's not so much a surprise as something that was important. So where does hemoglobin absorb efficiently? So if you now look at the graph of the scattering, what do you notice in that range?
So oxygenated blood absorbs more than the other in the range.
Yeah, so that's you may remember that if we had from the causality Kramers-Kronig relations, that if we had an oscillation in the absorption spectrum, that would correspond to a peak in the absorption spectrum, that would correspond to an oscillation in the real part of the refractive index, and the other way around. So what you see, and now what you do here, what is done here is that this oscillation in refractive index is plugged in into mean theory, and that apparently translates into an oscillation, to some swinging behavior around these same values. So if there, so the giveaway of the takeaway here is that if there is a huge absorption peak somewhere for a material, then you can also expect that there will be large scattering changes there as well. So that's basically what you see here happening. Any thoughts comparing this beautiful theoretical data with something more experimental?
It appears to have the tip around the same wavelength.
Yeah, so I was really happy with that. So that's true. The amplitudes are different. I guess that can have multiple reasons. They could be off. We could be off. That's all we can. But the difference is pretty large. So okay, going now to the anything that you notice from the or about the values. Yes. It's a little bit related to the discussion that we had about the size of the. So what happens if you have a phase function, or if you have a particle that scatters light predominantly in the forward direction? What is the anisotropy value going to be? Trending to be? So does that correspond to a high or a low anisotropy? Do you remember what the maybe that is the better question? Does somebody remember what the definition of the scattering anisotropy was?
It's the mean value of cosines.
The mean value of the cosine.
So it's scattered only farther direction than the V1.
Yeah.
So yeah, that's the maximum scattering.
Yeah, exactly. So if everything would be scattered in the total forward direction, then the scattering angle would be 0. The cosine of the scattering angle would be 1, and the average would be 1. So that implies that if the light is predominantly scattered in the forward direction, then that will correspond to small angles, will correspond to cosines that are close to 1, so that the average cosine will be a number that is close to 1. And that is what you see here. So that this axis runs from 0.9 to 1. And so for almost all wavelengths, there is a pretty high value. So for all the wavelengths, by direct blood samples, the light is scattered. Okay. Then if you take a look at literature, people have, of course, also tried to measure these scattering coefficients, then you find quite a variety of results. So you see here graphs that are just applying the same criteria as we did a little bit before. You see the dips and the peaks, more or less around the wavelengths that you expect. You also see that some of these curves overlap, but if you look closer, then you see that they were measured almost at the same volume fractions. The metagraph is the volume fraction mean for blood. And then there are some curves like these ones that are really truly not close. But the reason is, of course, that they are measured at different volume fractions. So how would you so let's say that we want to unify these curves into a single graph. So let's say we take a normative hematogrid, 45%. How would we scale it? So let's say, so I have this, this is the data that I got from literature. So I have a measurement at 5%, at 0.84%, at 33, at 42, at, well, let's see the list for yourself. So let's say I would like to unify this into, I would like to scale all these graphs to a volume fraction of 45%. So one option would be to let's say, okay, so take the one at so the top one is 5%. I could say, okay, I can take the scattering coefficient divided by 5 and then multiply it with 45. Would that be allowed? Would that be wise? The answer is implicit in the question. That is, it's true. It would not be wise because simply because of this nonlinear scaling that we have discussed with volume fraction, with concentration. So if I would scale linearly, I would just step back on that same straight line and then go back up. Whereas see what we've seen in the graph that had a scattering coefficient versus volume fraction is that the actual relation was at least not linear at the very least. So scaling that linearly would probably be a bad idea. It would not give you good results. So if you would, I don't have the graph here, I think, but if you would do that on this data, then the graphs would be all over the place. If you do take into account this nonlinear scaling, and you can estimate that theoretically how that should be represented in this graph, then you can see that there is, I mean, it's not perfect, but there is a fairly good degree of overlap between the measurements done at different concentrations, and then scaled to this normative 45%. So from that data, from that experimental data from different groups, you can calculate an average that is shown here in black. Then if we compare that average to the theoretical predictions, so really again based on absorption comes kind of mean theory, you see that it's not the same, obviously, but the range, the ballpark is pretty good, and the features, so let's say the peaks and the valleys of the spectrum occur at the same wavelengths. So we're actually quite happy about this. Okay, I want to conclude this topic. So a few questions for you to mull on. So we can do it now. You can also take this home. But these are the things that I do want you to have an answer to. So what? So very quickly, if I say what is dependent scattering, what's your answer?
Scattering was dependent on the structure function.
Yeah.
So with parents taking into account.
Exactly. Yeah. So dependent scattering is scattering where you take where the structure factor is included in the analysis, and the structure factor takes into account the interferences between the different variables. Good. The pair correlation function. Now we spent quite some time about that, so I'm not structure factor that also important one. How are the pair correlation functions and structure factor related?
Transform.
Yeah, so not exactly the Fourier transform, but formalized in the slides, so you can find it. But it is a Fourier transform, kind of. And then finally, that also we saw a couple of times. So if we make an extended expression for the scattering coefficient, at what point do we include the structure factor? Yeah, that was the integral of. What was the original argument of the integral? So the structure factor is in there, but what is also in there?
Yeah.
Phase function, yeah, you meant to say something. Yeah, so the integral of the phase function. So if the structure factor is not there, you would integrate over the phase function, then the result is just one unity. But if the structure factor is there, then the result will be different, and that causes the whole scale. All right. Let's take 10, and then yeah. Right. Let's continue. So it may seem like the topic is switching a little bit because it is a new presentation, but in fact, that I think it is not so much the case. It is also 2021, as you see. So I have 3 more things basically for today. Rayleigh Gans scattering, yet another scattering formalism that I want to spend some time about. Then scattering by continuous random medium. I'm not going to spend too much time about it because that is also a topic of your assignment. But you will see how that works. Switch. Yeah. So the perpetual question is, at what scale do we now actually describe this interaction with light emission? I've defined before kind of these 3 scales. We can look at the molecular level, or even smaller at the dipole level, or at the level of the particles, a particle that is well defined compared to wavelength set. So you can actually define a good solid dimension to it, or you can scale it up even further and look at not just particles, but bulk tissue volumes, etc. And what we have done up until now is basically trying to bridge these 2 domains a little bit together. So we had me theory. Okay, let's say me theory to describe the scattering properties of single particles, and then we used that model of not just a single particle, but of many of these single particles as a model for the scattering or the interaction on this larger scale. And then we found that we had to include this structure factor, for example, to make that properly work. So even though we got some results, and the results were plot, the thing that the example that we finished with before the break shows that it may not be perfect, but at least it gives some results that are they're not totally wrong. Let's put it that way. But still, the question is, can we do better? Can we find other approaches to bridge these gaps, or to change these to use these different formulas? So at a smaller scale that we discussed already a couple of weeks ago, is Rayleigh scattering dipoles. So if you calculate the scattering by a dipole, that would give you the same result basically as what Rayleigh derived for small molecules in the air. So that's pretty well worked out. I have put a small clip on the canvas for not a small clip, so that's a huge clip actually. That actually theoretically derives this way. That is, if you're interested, you can take it. Not necessarily part of the course. I do want to show you the results, of course, the outcome of that. So if we look at dipole scattering or small angle scattering, then we can express the scattered intensity, on the left-hand side, is of course proportional to the incident intensity. And then, there is some familiar scaling relations. So the scaling with 1 over r. What does that mean? R squared. Sorry, what does that mean? Intensity as a function of distance r scales with 1 over r squared.
a sphere.
It's a spherical outgoing wave. So you have a small particle here and that scatters. It's a spherical outgoing wave. So that is the K was the wave number to pi over lambda. So that means that the intensity here scales with lambda, or inversely with lambda to the fourth power. That is a characteristic of Rayleigh scattering. So you see that there. Also, there is this cosine squared theta term. So it is the angular dependence is given by that term over there. Do you know what alpha is? I mentioned it yet, but it's the polarizability. It is basically the ability of a molecule to form dipoles. So if depends on the charge distribution. If it's very tense, then a molecule cannot form dipoles. And if it cannot do that, they cannot oscillate, and then the scattering strength will be low. If it is loose, it can easily form dipoles, and then the scattering will be higher. So that is expressed in the polarizability. We can use we can take this equation and try to press it into form that separates total scattering strength in terms of the scattering cross section and the redistribution of the light in terms of the scattering coefficient phase function. So if you take these two equations and if you compare them, or if you then we have this exact I think assignment actually. So the phase function or the directionality is proportional to that term that has cosine squared plus 1. If you normalize that properly, then expression is given there, 3 over 16 times pi times cosine squared theta plus 1. Combining that with the previous ones allows you to isolate the scattering cross section by 3 times wave number to the fourth power and then the polarizability. So these are the classic results from Rayleigh theory. But now let's scale up. So I'm just showing them because I'll need them later on a little bit. So now on a larger scale, on a particle level, we had me theory, of course, but that was valid for spheres. So that's a big limitation. That if you know that you have a complex medium that is maybe composed of particles, but at least these particles are not going to be spheres. So let's see if we can do better there. And if you want to do better in any optics problems, then you have to solve Maxwell's equations. So here we are again. So in this formulation of Maxwell's equations, we have the properties. So I'm pretty sure you're familiar with how they look like. Sometimes they are in terms of the electric field strength. Sometimes they are in terms of the electric displacement D. This is a little bit of a mix. But the relation between the field strength and the displacement is given by the permittivity epsilon. That is also a complex quantity. This is epsilon is defined for a medium. So now the usual separation step is to express epsilon then as an absolute part that is valid for a vacuum, and then a relative part that is valid for that medium. So that can be the relative permittivity. You can go through your textbooks. That is the relative permittivity is then related to the susceptibility here. So you can make all these kinds of separations. You can write this displacement as a function of basically the vacuum response, so epsilon 0 times the electric field strength plus polarizability, polarization density. All these relations, all these quantities are functions of space and time. They're all complex, they have amplitudes and phase. So even though it already looks complicated here, in fact it is even more of a hassle to try to solve it. but still, we can do some things. So let's start with this polarization density P. So we can write displacement V as vacuum term, epsilon 0 times electric field strength, and then times this times the term that corresponds to the material. So polarization density P, epsilon 0 times G times E, is the total induced dipole moment per unit volume. So you're not looking at one molecule, let's say, or at one dipole, but at how effectively a chunk of material responds to incident electric field. We have used this one. So epsilon 0 times G is a response function. So that means that there's a real and imaginary part. That you can write clonal relations for that. So we actually already stole a little bit from that. If you now look in the Rayleigh theory, or in dipole scattering, there was also this deliberately small p polarizability, or the dipole moment, sorry, that was proportional to the polarizability in any field. So it is an expression that is similar to for the bulk. Which if you look at the terms that are in there, then that seems to suggest that there is some kind of relation between the susceptibility and the polarizability. Because it's a density, then probably the dipole density or the rho density should also be in there. So it kind of signifies how the molecular optical properties translate into bulk. But let's not dwell on that too much. What we do know is the relation again with complex refractive index. So top the complex refractive index M had a real and imaginary part, N and kappa. That would relate to the relative permittivity, epsilon R, through a square root relationship. We at some point express that as an epsilon R is small. We made a Taylor expansion of that square root. It relates to the susceptibility. It's in the same way. So M of 1 plus, and it relates to the polarizability of the molecule in that direction. So for the polarizability, we have here the complex refractive index, and here A is the size of the particle, so that is the volume. Basically scales with the volume of the particle. Not sure what the so the primes. The primes is I guess that is due to a comment I got last year. So I'm talking a lot about refractive index as being an absolute quantity, but usually it is assumed that it is relative to the refractive index of the medium that the particle is suspended in. So if you have a glass particle, for example, it can be an air, but it could also be in water. If we then talk about the refractive index of that measurement of that situation, then it's usually the ratio. So the ratio of the refractive index. Okay. So Maxwell's equations are absolute. We can apply them to the incident field, to the scattered field, but we can also apply them to the sum of the fields. So let's take a hypothetical situation where we have some material that is illuminated by light, and at some point, a distance far away, we pick up the response. That will be the sum of the non-interacting incident light and the scattered light. So like this. One key assumption here is going to be that the response is very small in amplitude with respect to it. So the scattered field amplitude is going to be much less than the incident field. that also means that that epsilon. So for the case of epsilon means that that the assumption is that epsilon 1 is much less than epsilon 0. That allows us to make kind of an expansion for epsilon as epsilon 0 plus 1, etc. Different terms, and then factor out the vacuum value, epsilon 0. Neglecting higher orders, that means that we can isolate basically the first order, epsilon 1. Epsilon 0 times epsilon 1 minus 1. With the expression for the refractive index that we had before, we can substitute that refractive index. Now all of a sudden we have a way, a little bit of a cheeky way, to insert the refractive index into these maximum equations. Manipulation. Okay, you're obviously all very familiar with the way to solve this equation to get the wave equation. So take the kernel of the top right hand equation for the equivalent. You can change the order of differentiations in time and in space. So substituting the lower right equation for the right hand side, use this. For the left hand side, we have a double curls. The curl to curl, that is a famous vector identity that you can also work out. Then this term will drop because D is proportional to E, so the gradient of E will be 0, etc., etc. You will get the standard wave equation. Now only the difference is, well, the standard, not really the standard wave equation. This is the total electric field, and this is still the electric displacement. So we have to do some manipulations. So you can expand this for the total field. So so on the left hand side, the Laplacian of E total field becomes the sum of Laplacians of the incident field and the scattered field. So that is the left hand side. On the right hand side, you can do the same thing. So epsilon appears in here, and a split for the source field and the scattered field. And then in the second step, on the right hand side, we can expand epsilon into epsilon 0 and epsilon 1. So we get a term that is proportional to epsilon 0 E0, epsilon 1 E0, epsilon 0 and the scattered field, and epsilon 1 and the scattered field. So if you now inspect these terms, then we had the assumption that that the scattered field was much less strong than the incident field, and that implied that epsilon 1 was also less strong than epsilon 0. Then we have basically strong terms in green that are proportional to the incident field and that are proportional to the vacuum value of epsilon. We have some weak terms that are either proportional to the scattered field or to epsilon 1, and we have one, basically very weak term that has epsilon 1 and the scattered field. So if you isolate these orders, then the green terms, the very strong terms, basically just describe the wave equation for the incoming field, E0. And grouping the first, let's say the first order terms together. So let's say for the scattered field, on the left hand side we would have the Laplacian of the scattered field over there. We would have something that's proportional to epsilon 0 and the scattered field. So that is not a very weak term, but a weak term. On the right hand side, only the epsilon 1 terms remain. So that will be combined like this. So this is a differential equation that is not necessarily usually solved. What it will say is that we have a function here, so the solution to this, to the left hand side, will be a function of the scattered field. scattered field as a function of the properties that is equivalent. On the right hand side, we have a function of the total field, because we still have E0 in the scattered field. So the question now is, can we solve this? Can we work this around so as to express the scattered field as a function, some other function, so that's why prime is there, of the total field. And if we can do that, if we can calculate the scattered field, then we can calculate the scattered intensity. If we can calculate the scattered intensity, when we can then again place this sphere around it, we can calculate the scattered power and calculate scattering cross section and scattering coefficient, etc. So then we're back in the game. I'm just going to show you the result. This is the solution. The integral is ugly. It has a phase term there. It's the T chi r. It is inversely proportional to R, which means that the intensity will be inversely proportional to R squared. So that is a spherical outgoing wave. So that's fine. Some prefactor. There's a volume integral, which has the wave factor, or some manipulations of the wave factor Ks. Ks is the direction of the detector, let's say. So the outer product of Ks with the outer product. Let's work. If we now compare that to our previous results, or our previous way of writing the scattered field, then even though it is complicated, there are some similarities. So there is some differences. There is the total field inside the integral. There is the incident field outside of the integral. There is scaling with R in both equations. There is a phase term exponential E chi R in both. Some normalization. There is a function that depends on angle, but if you take factors and you take outer products, that will also be a manipulation of angle. So there are some similarities that can be worked out, and we know our relation between the results. So if we combine these, we can do a few manipulations. So Ks would be the wave factor in the scattering direction. We can split that into a magnitude and a unit factor. So that is done here. So K times K would give us K squared. So it would be in S direction. Some other K appearing somewhere. So we make it flat. We can make the substitution for the refractive index for epsilon. So that would be this term. But we would still have the total field here inside the This would be based on unit vectors. So O would be the unit vector in the incident direction. S would be the unit vector in the scattering direction, just as they are defined before. So that is related to angles. So that is related to the S function. The problem here is the total field in the scattering form. So we are trying to find an expression for the scattered field. So again, on the top right is the form that we've used before, where the scattered field was proportional to the incident field, and then we had some factors that describes both amplitude and phase. So that is, but now we have a complicated integral relation that has the total field in there. That is not so easy to solve. It does have the refractive index, the local refractive index, as a governing property. These I'm not going to go into that too much, but the manipulation of the unit vectors, which will result in angles, also have some influence on polarization of the scatter plate. But that is, let's park that. the integration that is there. So the integration of the volume V. So basically, that is the volume of in which the scattering particles are, or the scattering material is contained. That will add a dimension of volume. That will be countered by the k to the third term before the integral. And that means that so even though the total scattered field is on the right hand side and the incident field there is on the left hand side, they do have the same dimensions. So working out this integral means that this fraction s in terms of unit vectors is going to be dimensions. So we are getting close to our function as of data. Now the trick is, and it is perhaps not surprising, is to just neglect the very, very big term. So the term that is proportional to epsilon 1 and to the scattered field, if we strike that from the equation, then the result is that the field inside the scattering volume becomes equal to the incident field everywhere. So basically, every volume element in the scattering volume sees the same incident field, sees the same field strength, and that's. I also said it a little bit earlier on that implies that there is no light that is scattered from one part of the volume that is being rescattered from another part of the volume, because that would not be true. With that, we can simplify the integrals a little bit. So instead of E, the total field inside the integral, here on top, we now have E0 inside the integral. That is no longer dependent on the spatial coordinates. You can take it out of the integral, which means that you can strike it on both sides of the equation. So then what's left is an expression for the function s. If we can also if we can also perform the integrations over the angles, so that would be or perform the manipulations over the angles separate from the integration of the volume, then a further separation is possible. So we can take S, so the manipulations of the angle, take it out of the integral. These terms are just constants. The integration of the volume would just yield a value phi, and then what remains of the integral, so phi there cancels this phi here. What remains of the integral is a volume integral, or Fourier transform, actually, as you can see, of the refractive index distribution over that volume. That has a name that is called a form factor. And we can simplify that. So that was a lot of manipulations to arrive at a result, but basically it is important, because basically what we see now is that we have an integral sum over values of the refractive index, and we know that the refractive index itself, or the factor within the integral, the scattering potential, so the refractive index squared minus 1, is proportional to the density inside the tissue. It's the density distribution inside the tissue. So if any changes occur due to disease or due to treatment or whatever in the tissue composition, that will of course be reflected in the tissue density. But it will not be complicated, but it will be reflected in the refractive index as well. Through this form factor, it will be reflected in the scattered field, and through the scattered field, it will be reflected into the scattered intensity, and through the scattered intensity, it will be reflected into the properties. So this is a link, maybe even between light scattering, so from a localized volume and the architecture of tissue. As you can see, this relation is a Fourier transform. So again, you could take the local distribution of refractive index and calculate 3D Fourier transform and get the form. I'm going to skip this. The form factors can be calculated for different particle sizes, shapes, so for rods, for discs, for spheres. So the exact forms do not matter here. The point is that you can look at. What I would like to do is make a comparison to what we did before the break. So with the model where tissue is built up of spherical particles, and these spherical particles interact with each other, or the light that scatters from them interacts with each other. We found this relation, this structure factor that was a kind of Fourier relation between the pair correlation function, which describes the organization, the placement of the particles. Link these two together. So for the form factor, you have kind of the same equation. So you have a distribution of the refractive index, which is more or less maybe more or less comparable to the distribution of particles in there, or particle distances in the medium. So that is in green. After taking the Fourier transform, so from the spatial domain to the Q domain, we get information on the scattering properties. So if you would do that, for example, for a spherical particle, then the form factor would look like this. So again, here too, it becomes a function of the scattering factor Q, so the factorial difference between the scatter plane factor and the incident plane factor. And you think, basically, you can derive some kind of quasi-analytical solution for the scattering coefficient. So again, looking at the model on the top right-hand side on the tissue level, if you would describe it as a collection of particles, then you would need the structure factor. Then you would need to structure factor to bind together the scattering fields, the scattering phases, the scattering phases basically of these different particles. With the equation. So if you would now try to look at some equivalence in these scattering properties. So for this Rayleigh Gans scattering, every volume element acts as a dipole scatterer, and you would need the form factor to tie that together to get the scattering of a single particle. If you have a single particle and you would like to describe the scattering by a volume, you would need the structure factor to tie that together as well. And both of them are these Fourier transform kind of relations between spatial distribution of either refractive index or of particle positions. So there is this seemingly equivalence in these formalisms as you scale it up. But still, that's the. Before I go to the next slide, still it is this picture of modeling tissue as discrete particles. So here, at some point we started here where the particles were well defined. You could calculate the structure factor, you could go to the volume. If you start a little bit earlier on downstream with this Rayleigh Gans theory on Maxwell's equations, you would maybe start here with the form factor and end up here, but still need to take this step. So the problem is not really solved. And that is where yeah, where the new theory comes in, basically the new way of looking at tissue. So not as discrete particles, but more as a kind of a continuous soup. So let's say take the blender on this soup and then look at the properties. So there are no distinct particles anymore, but we describe the tissue as a let's say continuous variation of refractive index. So the refractive index is spatially independent. It's a function of R. But it is not. So if you would have a particle, it would have some value inside the particle and some value outside. And now it is just a continuous fluctuation. The assumption is still that this relation between density and refractive index holds. So m squared was proportional to. But because it is continuous, because it is now a distribution, we need different parameters to describe it. So, and the refractive index will now be described by, let's say, an average value and a variance. So a mean value and a fluctuation of that. Because it is now a random quantity, we cannot just calculate the square. We want to average that over different possible values. So instead of calculating this squared, we now calculate the so-called correlation function. So you multiply with the spatially shifted version of itself and then average that over the volume. That means that the equations change a little bit. So instead of the Rayleigh Gans equation where m squared was included, we now have you end up with an average. Instead of m squared, we have this correlation function. So the formulation does not change that much, only the inclusion of the refractive index distribution changes a little bit. If we look at the optical properties, so let's say the scattering coefficient. Scattering coefficient was the volume average of the scattering cross section that is on the left hand side. We could calculate that by, for example, having scattering cross section split out under the different angles and then integrate that over the different angles. Is it clear? So this is not this one is not a property that I introduced earlier. But so the total scattering cross section basically is all depicts all the light that is scattered in any direction. What happens inside the integral is that you take one step back. So okay, let's look at how much light is scattered into the different directions, and if we add all the angles back together again, then it should be total scattering cross section. So that is the term within the integral. The result of treating this as a continuous random medium instead of discrete with particles is given here. So this is the factor within the integral. There is a blue underlined in blue is the scattering pattern of a dipole. So basically, what it says is that all the individual scattering centers, volume elements are dipoles, and they are tied together. In this case, by this red function, which is the spectrum, the power spectral density of the refractive index correlation. So the refractive index correlation was this m times. The m of so it is the zero as function of theta and phi. Of course, you can this is angles in polar coordinates, so we can also write that as a function of the scattering factor q. So that was the factorial difference of the incoming and scattered wave factors. That can be defined in 3D, so it should be equivalent. And then the function v is defined again through a Fourier transform relation with q, with r spatial coordinate of this refractive index correlation that we saw. So this is the new approach, the new theory. Basically taking the same concepts from, so starting with Maxwell's equations, you get this overall governing scattering equation. If you assume that your scattering volume is a particle, you will integrate over the particle and get the result. But now, because you no longer assume that this particle, but it's a continuous fluctuation of refractive index. What you need to fill in into that expression becomes more complicated. Then, of course, the question is what kind of correlation function would you need? How do you describe that? This has been suggested. So just giving you this as an example. This is the so-called Whittle-Mattern family of correlation function. It is a family because we have a parameter beta that can tune it a little bit. But here are, so that is the green parameter. The sigma is the variance of the refractive index. So that basically tells us how strongly the refractive index fluctuates. The correlation length is a spatial measure of how slowly it fluctuates. So basically these parameters then describe how spatial fluctuation of the refractive index will take. There is something to be said for this approach, even though it is very different from the classical approach to light scattering. The statistical properties that we can derive from this. So let's say we were able to measure this correlation function. The variance of refractive index is something that you could measure from pathology. You could take a pathology image, look at each and every point what the refractive index is, and you can do it by a transmission measurement or by a reflection measurement. But the spatial variance of this refractive index can be obtained from that. Likewise, if you have this image and you have these values, then you can just see how strongly or how slowly or fast it varies as a function of spatial distance. So this correlation length can also be determined from exactly the pathology image. So the pathology image is what currently is the gold standard for diagnosis. So the promise of this approach is that if we can derive these parameters, they may be much more valuable than, let's say, an absorption coefficient or a scattering coefficient. So that's the promise. The challenge here is that this whole concept of looking at media over scattering is so basically so new, so fake that we have no easy way of connecting it with our standard way of looking at things. Our standard way would be to, if we have a new instrument and we want to assess its performance, we would take these spheres from which we can calculate what the scattering properties are. We would put them in a solution where we know the volume fraction, and we would do a measurement. And then if it fits, then we say it's calibrated. So here it's much more difficult. So how do you make a calibration? How do you make a calibration phantom or calibration material with a known correlation length? So even though the promise is big, the experimental way of validating it, if it actually works, is quite a challenge. So one technique that can help here is phase microscopy. So phase microscopy actually does measure the local refractive index at each point. So if you would take an image like that, you could just calculate the spatial statistics, like a correlation length and variance. So that could work. That is, so this approach is relatively new. So this is a paper from not even 10 years ago, where it is actually for the first time it is really introduced into our field. So not that long ago. So there's a continuous random medium instead of a discrete. What I'm interested in, and I can't help telling you this, is basically so where our research is at the moment, or our clinical research is at the moment, is here, down here. So we have we can measure microdoses. We measure scattering properties. We quantify them with OCT. Then we make a phenomenological connection with disease. So we measure something. The pathologist looks at the specimen that corresponds to that, says, okay, this is, let's say, cancer grade 2. Then we say, okay, apparently cancer grade 2 corresponds to the optical properties that we measure. Of course, you build up statistics for that, and that is the way it goes. So we are working here. The pathologist is working here. Tying that together quantitatively is really difficult. So to take these steps, we have done a couple of things. So from the pathology side, what helped immensely is to actually do digital pathology, to actually scan these slides, not just look on the microscope and then store them somewhere, but digitally scan them so that you can do image processing. So you can have an AI algorithm on that. So to get more information from that. So that is from the pathology side. From our side, we have tried to better understand how these scattering values that we measure come about. I've talked a lot about discrete random media, but perhaps the step bridging that could be these continuous random media. So I'm very interested in this approach, but also the difficulties in validation and in calibration. They are really these are really of interest, and that's actually the reason why I want to throw this to you as an assignment, as the second assignment. So I'm going to explain what I would like you to do. And so again, the introduction is then, at what scale do we describe light scattering? So for a dipole, you could take a very small particle. Rayleigh theory would hold. For a red blood cell, you could take a spherical particle that has a certain size equivalent to the red blood cell, and then V theory would hold. And for blood tissue, vasculature, whatever, you would take a bunch of particles and you would need the structure factors and so on to make that work. The applicability of scattering is of course a little bit questionable, because scatterers in tissue are not spheres, and also if we look at maybe non-scattering or foam factors or structure factors, they are all approximations, and every step that we need to take, there was an approximation. So in the end, we take many approximations. For the purpose of structure factors. So there is, with the standard approach, there is enough uncertainty. So then what we'll try to do is, and a little bit summarizing what I was trying to tell you, is to model tissue as a continuous spatial fluctuation of refractive index. So not just particle, no particle, particle, no particle. That's a continuous fluctuation that will apply to our earlier methods. So where we described the angular redistribution of light as a function of theta phi in S. So from Maxwell's equations, we can get we can get a function that in the firstborn approximation allows us to get an expression for S, and in the case of single particles, we could solve S by calculating the form factor. So we would have a dipole scattering pattern, volume of the particle, and that a form factor that would describe how a particle would behave. Calculate the coefficients. In case of the random median, we would have to take averages, but the same factors kind of appear. So we still have a dipole scattering pattern. So the ultimate infinitely small scattering volume is a dipole. Only the function that ties it all together is different. So here, it's power spectral density. But again, with the same arguments. I do have to. Yeah. So I'm gonna. What I will do is I will give you a research paper by Rogers. That is that you saw already. He has a section in there that he calls validation, where he calculates the scattering properties of basically of spheres using the classical formalism and using the formalism of a discrete of a continuous memory. The word of caution is here. So the scattering coefficient is by definition is the density of scattering cross section. So we calculate the total scattering cross section of the volume. We divide it by the volume. In case of the spheres, that meant that we could basically just the ideal case just calculate the scattering cross section of a single particle and multiply with the density. But we can write that. We could write that this density, volume density of total scattering cross section in this form. For the continuous random medium, you will find that there is an expression in the paper. It looks like this, which actually calculates this same thing. So what we calculate here is the same density of scattering cross section, only still being split out over different angles. So what we still need to do here is integrate over angles, over the 4/12 angle in order to get the true scattering coefficient. So the assignment basically is to work a little bit with this formalism. So what he did is indeed like I said, so take a suspension of spheres and calculate that using B theory and then also using his formalism and then compare it. These are the equations that are in the paper. I'm just going to show them to you so that you know that what you can expect. The equation over there is the equation for the density of scattering cross section. So in the way that I've written it in the previous slides, that would be the same as the expression down there. You need to integrate this over angle to get the scattering coefficient. The question is going to be what is the scattering coefficient? So this would need to be integrated. That function that ties it, so you will also recognize the dipole scattering pattern. So it's the square data in 2005. The function that ties it all together is also given here. CV is the volume fraction, and M is the refractive index of the medium, and S is the refractive index of the sphere. A little bit confusing is that he uses symbol K where we used symbol Q. Take care of that as well. But in effect, this is something that can be combined and can be integrated over angles. what I would like you to do is to do that numerically, of course, not analytically, because that's possible. So you can use, I don't know, what if you're fluent in Python or in MATLAB or team up. It's fine with me. Try to implement it. Try to find scattering cross section or the scattering coefficient as a function of volume fractions. The problem I have with his validation, as he calls it, is that he compares me theory with his new theory, with his continuous random medium, but he does not include structure factors. So he just calculates it using me theory and scales linearly. Whereas we have found that actually, if you have many particles, you should include that structure. So my goal for you is to try to find out if we do include the structure factor, can we then still, or is the validation better than in that case? So this is a try that I did earlier on. So this is on the horizontal axis, it is volume fraction. On the vertical axis, it is the scattering coefficients in per millimeters. It's small numbers because the particle is small. The refractive index difference is not that large. If you use me theory, just me theory, no structure factors at all, then the dotted lines, the blue dotted lines, would be the result. So a linear increase of the scattering coefficient with volume fraction. If I include, for example, the Perkus-Yevik structure factor that I've been using for this class, then I would get this blue line. So this no longer a linear increase; it will be sublinear. The values will be lower than the linear increase. That's what we saw earlier. The formalism of Rogers, the continuous random medium, gives the green line, but it's not the same. The question is where is this? Where does this go wrong? So I used me theory, which should be valid for all wavelengths, but we could also try to use the somewhat simpler Rayleigh theory. So the question is, for example, what would happen if we would use Rayleigh theory to calculate the scattering coefficient as a function of volume fraction without including the structure factor? That would be the third box that is, and the first box that is not ticked. And then if we would include the structure factor, how would that look? So how would these graphs then fall in this range? A second simulation with a slightly larger particle basically gives more or less the same trend, but even a little bit more pronounced. So with me theory alone, you will see a linear increase. For me theory with the structure factor, you will see a sublinear increase. So there is still an increase. And the continuous random medium approach is somewhere in the middle. So my question to you is can you fill in the blanks? Can we do a calculation where we calculate the scattering coefficient either using just Rayleigh scattering and using Rayleigh scattering with the structure factor, which is probably going to be the better solution because we expect that. So the structure factor that I would like you to use is given here. So Q is again 2 times K times the sine half theta. F is the volume fraction. D is the particle diameter. The variables, I think. Just to be sure, this is we had this graph for the different pair correlation functions, and we knew that the structure factor was the Fourier transform or the Fourier transform relation of that pair correlation function. For low volume fractions, the structure factor, the pair correlation function is a step function, so the black line here. Then we would get the the red, the red curve here. The analytical solution for the structure factor would be the first terms of that equation there, the lines with red. If we, but that would be a good approximation for low volume fractions. For higher volume fractions, we saw that the probability of finding a particle next to the particle itself increases. So a way to model that would be to include a delta function here. So then the model pair correlation function would look like a step function, but only with an additional peak at exactly separation of the diameter. If you do that, if you include that, then that second term here appears. So that is a slightly better approximation for the so slightly better approximation for the pair correlation function, and therefore also slightly better approximation. So this is the one that I'm like. So then basically the question is that so take the size, the wavelength, the reflective indexes that are in these slides. That will be on campus, of course. You can also pick a few yourselves. That is fine with me. And what I would like you to do is that really make this is not don't make it too big. Just overview or report or that describes the problem statement. You can get that from Rogers. You can get that from these slides. The methods, that means the relevant equations, the equations that you needed to generate graphs. And also, what I would like to see is a discussion of the differences between the formulas when there is a difference, of course. This is already a difference. So can you hypothesize where that comes from? You can find reasons, and again look at the paper because there is a lot of information there. See where it comes from. So that is what I would like you to work on. Again, please do this if you want. You can do it alone. You can do it in groups. That is fine with me.
The final report that can also be in groups, or you can just work in groups and write.
No. That the report as well, of course. Yeah. Okay. And really, this is a bit of an experiment for me too, because I actually don't know really. I've tried to simulate it, of course. So I will put my results. I will put my results on the campus as well, so you can just make the graphs using that. But I'm just curious how it will work out. So it's yeah. So I guess I'll put the paper on Canvas. So I guess the first step is just to look at the paper, and see if there's if that's clear, and if not, then let me know. Yeah, no, I'm not. Yeah, I will have to set a deadline because that is what Canvas wants me to do. I will set it at the date of the exam. Yeah, so I would say. So I am going to give you a third assignment somewhere next week. So plan for a week or 2 weeks. I'm not going to be strict about deadlines. I don't like that.
And regarding the group size, there should be around 2 again.
Same as before. Try to diversify a little bit, but if it does not. Again, for that too, I don't want to be strict about that. If you have a group, good working group, then. So the only thing is, it's your own. Basically, it's your own choice. So if you work in a group, you will get the same grade. That's it. And the final exam is individual. Bueno.
One.